Now, sometimes we're going to get questions that are for integration that are going to be back into this form, the derivative function over the function, which we know integrates to a log function from the work we do in 2UNIT. So we're looking at this example. That's, you're going, yeah, that's pretty easy. Yes, we know it's easy, but that's an example of what we're looking at. But the questions you're going to face are not as easy as that. So when we look at this situation again, we can use a bit of a substitution to try and do this. Now this one's a little bit harder as such, and relies on us using our table of standard integrals to do this sometimes. Because if you have a look at that function when we come down to, like we can see that we're going to have something like a derivative of a function over a function as such there. So if I do a substitution here of letting u be equal to e to the power of x, so it gives us the idea that we get e to the power of x minus x dx with a negative out the front, becomes our du, and we've got the square root of 1 plus u squared there. Now, if we go to our table of standard integrals, then from this table of standard integrals, we don't have a rule that we really done that, and this is one of the last couple of rules on the table of standard integrals. So go check this out. That would be the integral of that function there, the square root of 1 plus x u squared. It's not an inverse trig function because it is plus and not minus. So you've got to be able to use, probably more so in extension 2 than any other courses, the table of standard integrals to be able to use this one. If you remember this one off by heart, well done. I don't remember it off by heart. I'd go back to the table of standard integrals every time to be able to do that. We get u, and then we're able to substitute our u back there. So this one here, we haven't used a substitution for this one, and it's a definite integral at this time, so be wary if we get a definite integral. Derivative of x times 1 over x times log of x. Now, we recognise we can write that as that function, or we write it like that, or the derivative of 1 over x, 1 over the x time over log e of x. So in that form is what we're talking about. So by our manipulation there, which is the derivative of that function over the function. So it's really the log of x. So again, we have that recognition. We're able to get back to that function there. Again, it's being able to manipulate the algebra to suit what we need and be able to use what we need there, and we're able to recognize that it will integrate to a log function and then solve it as we've done before. Also, we need to recognize the transformations, and again, using our table of standard integrals, this time to do our inverse trig functions. So again, I've solved it using a situation where we've got a substitution on this side, but recognizing that this is just in that form of the derivative of the function over 1 plus the function squared. If we can recognize that, we can go straight back to inverse tan of x squared. That's going to be the derivative there. So again, we're recognizing the function that forms the integrand take that will be of standard integrals, which comes back to an inverse trig function. So e to the power of minus x 1 plus e to the power of minus 2x. So something like that, again, is an inverse tan function, derivative of the function over the 1 plus the function squared. So again, we do need to do a bit of manipulation there, because the derivative of e to the power of minus x is minus e to the minus x, so we do have a little bit of manipulation to do. But again, if you want to do it using a substitution, then you feel free to go ahead and do that. That's not a problem at all. This one here, again, we're doing a substitution. X to the power of 4 dx over 1 over x to the power of 5 plus 1 all squared. And this is really a reversal of the chain rule type situation again. So we can see how it works out there. Again, we're got a reversal of the chain rule, but I've done it with a substitution. and be able to solve through to get back to what we want. And they're not the prettiest of ones because it's the square roots there, so it's not looking very nice. That's where sometimes our substitution comes in handy, because they're not pretty and easy to see. Here's one again, e to the x over 1 plus e to the 2x. Again, we're in that form of e to the x dx over 1 plus e to the x all squared. The function, derivative of the function over the function 1 plus the function squared. Again, this one here, use the substitution. Again, you could have used a chain rule there to solve that one and get down to the function expression there. This time here, this one's a little bit harder to see, but if you let u be equal to the inverse tan of x, then du is equal to 1 on 1 plus x squared. Now, if we look at that, that should have a dx there. So really what we're looking at, again, is a reversal of the chain rule, because if we differentiated inverse tan of x all squared, we'd get down to something in that form. We'd have a 2 out the front, but we'd get down to that form because the derivative of inverse tan of x is 1 on 1 plus x squared. So really we've got the function times the derivative of the function. So we're going to integrate the function itself. So it is a reversal of chain rule. It's easier to see with a substitution there. But again, if you can do it without a substitution, you're going very well. Again, this one here, we've got x on square root of 9 minus x to the power of 4. Again, if we recognise that the derivative of the function of is 9 minus the x power x squared, all squared, would be the derivative there would be with 2x. So we manipulate it to get a half out the front. So we're talking about this form of our standard integral. There comes down to inverse sine of the function of x on a, and that's where we've gone back to there. Again, use a substitution, and if substitution helps you, then that's well and good, and you're able to solve it that way. This time, again, this is like the tan one we saw before, e to the power of inverse cos of x. Well, again, if I use a derivative here, so substitution and then get the derivative, and have du is minus 1 on the square root of 1 minus the square root of x dx, we can start to see I can rewrite it like that. But again, the derivative of that is that part there. So it starts to be a situation of reversing the chain rule. But again, we can do it with substitution, not a problem. X times 1 minus log x all squared, and again recognizing that the derivative of log of x is 1 on x, so that's where that 1 on x would come into play. But again, I've done it with a substitution with du equals 1 on x dx. So there's the 1 on x dx there, giving the du on the u squared, which is 1 plus the log of x is u. We can integrate that and come down to our function there. But again, it's a reversal of the chain rule all the time. Done a little bit easier this time with a substitution. So e to the x, sine e to the x, and this is a case where we know the derivative of sine e to the x would involve an e to the x there. So again, reversing the chain rule, sine integrates to cos, and the e to the x would become absorbed there because it was the derivative of the function, which just gives us the minus cos e to the x. Again, I did it using a substitution, which was quite easy. And again, another one like that, sec squared of x, square root of 1 minus square root of tan squared x minus 1. Again, that's back to, if we have a look at our table standard integrals, there's one of those other ones that are not ones we've used anywhere else in any other course. So the square root of u squared minus 1, it's close to the inverse trig function, but it's not. It actually integrates to a log function. So I've done a substitution there, and again, tan sec squared, we should recognize that relationship to be able to say, well, that's going to give me a nice substitution, and be able to integrate it using our table of standard integrals. and then put our substitution back there. So again, there's more of those ones involving the chain rule, and where we can start to use the chain rule if we can recognise it. Otherwise, doing a substitution that's necessary. Also using the table of standard integrals to either see an inverse trig function or a log function if we need it, or these other ones that are down the bottom of our table of standard integrals that we haven't used before in other courses, but recognising that if it's in that form we can go back and use it. So have your table of standard integrals handy as you are starting to do extension to integration. As I said before, it's probably more important here than we have seen in any of the other courses for the table of standard integrals, because of some of the ones we're going to use, like this last one here.